Welcome to The Explainer. Today we're diving into a really powerful mental model, one that helps us think about evidence and what we believe. It's a way of reasoning that trips up pretty much everyone, even doctors and data scientists. And if we're not careful, it can actually trap us inside our own assumptions.
Okay, let's just jump right in with a pretty high-stakes scenario. This is a classic little paradox that really shows how easily our own intuition can steer us completely off course when we're dealing with uncertainty. So just imagine this for a second. You go to the doctor and you get a positive test result for some nasty disease. Now, the disease itself is super rare. It only affects about 1 in 1,000 people. But the test is really good. It's 99% accurate. So you test positive. What does your gut tell you? What's the chance you actually have it? If your brain immediately jumped to 99%, well, you're in good company. That is by far the most common answer people give. And it seems to make perfect sense, right? I mean, the test is 99% accurate, so the result must be 99% certain. But, and this is what's so wild, that intuitive answer isn't just a little bit off. It is dramatically, fundamentally wrong. The real answer isn't even in the same ballpark as 99%. And to see why, we have to completely change how we frame the problem. So the trick here is to stop thinking about abstract percentages, which our brains are kind of terrible at, and start thinking in concrete numbers, what we call frequencies. So let's imagine a real group of people and just see what happens. Okay, let's take a nice round sample of 1,000 people. Since we know the disease affects 1 in 1,000, we can expect that in this group, exactly one person is actually sick. And that means the other 999 are perfectly healthy. This is our starting point, our baseline. All right, now let's give our test to all 1,000 people. For that one person who's actually sick, the 99% accuracy means they're almost definitely going to test positive. So that's our one true positive. But here's the kicker. What about the 999 healthy people? The test has a 1% error rate, which means about 10 of those healthy people will also test positive completely by mistake. These are our false positives. And this brings us right to the heart of the whole puzzle. Just look at the group of people who got a positive test result. In that group, we have a grand total of 11 people. You've got the one person who's really sick, and then you've got 10 healthy people who just got a false alarm. So let's ask our question again. If you're one of those 11 people holding a positive test, what's the actual chance you're the one who's truly sick? Well, it's 1 out of 11, which is about 9%. Just think about that, a world of difference from 99%. Because the disease is so incredibly rare, even a really accurate test ends up generating way more false alarms than actual real cases. Now, this way of thinking, where new information adjusts what you already believe, it's not just a cool brain teaser, it's actually a formal system for reasoning through uncertainty. It's called Bayesian reasoning.
And it basically works in 3 simple steps. Everything starts with your prior probability. This is what you believe before you see any new evidence. In our medical case, the prior was that base rate, that really, really low 1 in 1,000 chance of having the disease in the first place.
Then you get some new information. That's the likelihood. This is all about the strength of your new evidence. For us, that was the 99% accuracy of the test. It's a strong piece of evidence for sure, but it's not the whole story.
And when you combine that weak starting belief, your prior, with that strong new evidence, you get your posterior probability. This is your new, updated belief. The evidence did its job. It pulled your probability way up from 0.1%, but because your starting point was so low, it only managed to pull it up to that surprising 9%.
So the single most important takeaway here is this. Evidence doesn't just exist in a vacuum. It doesn't create a belief out of thin air. All it does is update the beliefs you already came in with. A really strong piece of evidence can't just wave a magic wand and erase a very, very weak starting position.
And this whole idea actually leads us to a much bigger, kind of mind-bending idea about randomness and knowledge itself. This quote really gets at a powerful concept. What we see as randomness in the world, it's not necessarily some fundamental property of the universe. A lot of the time, it's just a reflection of our own missing information.
Think of it like this. The universe is just insanely complex. And we are, as the scientist Stephen Wolfram puts it, computationally bounded observers. We simply don't have the brain power or the tools to track every single variable. And because our information is always incomplete, the world looks uncertain and random to us.
And this is exactly why the physicist E.T. Jaynes said that probability is the logic of science.
Science isn't this grand quest for absolute 100% certainty. It's a Bayesian process. It's about building models of the world and then just constantly updating those models as new, messy, incomplete evidence comes trickling in.
But here's where we get to the final twist. What happens when this powerful, logical tool gets used against us by the most important and most fallible component in the whole system, our own minds? What if this whole system, which is designed to help us break free of our biases and update our beliefs with new facts, actually ends up doing the opposite and traps us inside of them? Well, this is the whole idea behind the Bayesian Trap.
Here's how this dangerous feedback loop works. Let's say you try something new, and you fail a couple of times. Those past results start to build a really strong prior belief in your head, I'm just not good at this. And because you believe that so strongly, you stop trying, you stop experimenting. And because you stop trying, you keep getting the same result, nothing. Which you then see as proof that your original belief was right all along. You're stuck.
And this points to the single most important rule if you want to be a good Bayesian thinker. You have to avoid absolute certainty. You can never let your prior belief become 100%, or 0% for that matter, because the math is clear. If you do, then no amount of new evidence, no matter how powerful, can ever change your mind. You've basically shut down your ability to learn.
So the big thing to take away from all this is that your beliefs are not reality. They're just a model of reality. And just like any good scientist, you have to be willing to get out there and run new experiments to test that model. So I'll just leave you with this question. What's a belief you've been holding on to, maybe a little too tightly, that it might be time to challenge with a brand new experiment?